Hello everybody, today we're going to have a look at Euclidean geometry. First we're going to take a look at a bit of revision of grade 11 theorems. And we've got theorem 1 which states the line segment joining the center of a circle to the midpoint of a chord is perpendicular to the chord. So we have if AC is equal in length to CB, then we've got that OC is perpendicular to the line or to the chord AB, and the converse in this case is also true. So if we had that OC is perpendicular to AB, we could infer that then AC would be equal in length to CB. Moving on to theorem number 2. Theorem number 2 states that the angle subtended by an arc at the center of a circle is double the size of the angle subtended by the same arc at the circumference. Looking at the first diagram we've got over here, we can see that basically this theorem states that the angle subtended at the midpoint of this arc is twice the size of the angle at the circumference. And looking at the second diagram, we've got the similar case over here where we can see the angle at the midpoint is twice the size of the angle at the circumference. And again, the third scenario here is exactly the same, just drawn differently, and you might see all of these in a question paper. We can see that this arc at the midpoint, the angle of this arc is twice the size of the angle at the circumference. And just how we can see how these arcs are formed, it will always be two lines going from the midpoint to the edge of the circle and then joining back at one single point there. So you can see we've got our two lines here and they join at the edge of the circle again at the same point. Looking at the second diagram, we've got our two lines here and again they join at the same point. Two lines going from the center and the third one meeting at the same point there. Theorem 3 states the angle subtended at the circle by a diameter is a right angle. We say that the angle in a semicircle is 90 degrees. Thus, in the diagram we have here, we could say the angle C is equal to 90 degrees. Now, the converse simply states that if the angle subtended by a chord at a point on the circle is 90 degrees, then the chord is a diameter. Meaning that if we didn't know this chord here, AB, is a diameter, if we knew that this angle C is equal to 90 degrees, that would mean then that this chord is in fact a diameter. Theorem 4 states an arc or line segment of a circle subtends equal angles at the circumference of the circle. We say that the angles in the same segment of the circle are equal. So basically, if we have a shape like you have here that almost looks like a butterfly with all four of the corners on the edge of the circle, we could say that in this case angle D is equal to angle C. Likewise, angle A, even though it's not indicated on the diagram, is equal to angle B over there. So we've got angle B is equal to angle A, and angle D is equal to angle C. Before we continue and look at theorem 5, I just quickly want to recap what a cyclic quadrilateral is. So basically, a quadrilateral whose vertices lie on the circumference of a circle is referred to as a cyclic quadrilateral. So we can see that the diagram we have here, this is in fact a cyclic quadrilateral, since the vertices A, B, C, and D all lie on the circumference. And we also call that concyclic when the points are on the circumference. Theorem 5 states the opposite angles of a cyclic quadrilateral are supplementary, meaning they add up to 180 degrees. So in the diagram we've got over here, we could say that angle D plus angle B is equal to 180 degrees. Likewise, we could say that angle A plus angle C should also equal to 180 degrees. I'm going to pop the proof on the screen here, but I'm not going to be working through it. You're more than welcome to pause the video should you want to have a look at it. The converse of theorem 5 also applies. So if we have that opposite angles of a quadrilateral equal to 180 when you add them, then it means it is a cyclic quadrilateral. So in this case, if D plus angle B, like it shows in the diagram, equals to 180 degrees, then we know that it is in fact a cyclic quadrilateral, as we can see here. Theorem 6 states that an exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So if we take a look at the diagram here, if ABCD is a cyclic quadrilateral, which we can see it is, then we have that angle C1 is equal to angle A. So just again, that theorem states that the exterior angle of the cyclic quadrilateral C1 is equal to the interior opposite angle A in this case here. So the converse obviously also applies. That simply states if an exterior angle of a quadrilateral is equal to the interior opposite angle, then the quadrilateral is a cyclic quadrilateral. Theorem 7, 8 and 9 all involve tangents to a circle. Theorem 7 states that a tangent to a circle is perpendicular to the radius at the point of contact. So if we look in the diagram here, basically as I've written, if ABC is a tangent to the circle touching at point B, then the line OB is perpendicular to line ABC. And the converse obviously is true as well, which simply states that if a line is drawn perpendicular to a radius at the point where the radius meets the circle, then the line is a tangent to the circle. Theorem 8 states that if two tangents are drawn from the same point outside a circle, then they are equal in length. So basically we can see that we've got a tangent here AB and a tangent AC, and they were both drawn from the same point, thus we can say they are equal in length. Theorem 9 states that the angle between a tangent to a circle and a chord drawn from the point of contact equal to an angle in the alternate segment. Basically what that means is, if in the diagram that we see here, if CDE is a tangent to the circle at point D, then we have that D1, angle D1 is equal to angle A, and angle C2 is equal to angle B. So basically we can see here that angle C2 over there is equal to angle B over there, and we've got that angle D1 over here is equal to angle A over there. And again, I'm not going to prove this, but I will put the proof on for a few seconds, and I'm going to put two cases of the proof on. The first will be for when it is acute angles, and the next will be for when it is obtuse angles.